Good morning, everyone. Thanks for showing up today. We're going to be talking today about the central limit theorem and how to use it to understand the properties of sample means. Two brief announcements before we dive into it. First, don't forget that homework 8 is due this week, not Wednesday, Thursday, as usual. Sorry. And the project 2 checkpoint is due this Friday. You'll be working on that in lab this week. All right, so we've been looking at center and spread and the bell-shaped curve. And I gave you an intro to the central limit theorem on Monday. And then today we're going to work through this a little more systematically and talk through its applications. Yes, homework is due on Thursday. I'm sorry, I wrote the wrong thing in the slide. My mistake. Sorry to hope I didn't give you any heart palpitations there. All right, central limit theorem. So let's do a little refresher about the central limit theorem from last lecture. The central limit theorem draws a connection between the averages of a random sample and the normal distribution, the bell-shaped curve. The central limit theorem tells us about what the shape of the distribution is if you take a sample and you take the average of the values in that sample. And we care a lot about sample averages because we often care about the average of some number in a population. And then the way we estimate that is by taking a sample and using the sample average as our estimate of the population average. So it's useful to understand the properties of sample averages. That will help us understand how accurate our estimate is likely to be. Okay, so here's what the central limit theorem says. It says, if you have a sample that is large and drawn at random with replacement, then the probability distribution of the sample mean is roughly normal. It has a bell shape. So by sample mean, I mean the way to interpret that is that you take a random sample and take the average of the things in the sample, and that's called the sample mean. And crucially, the central limit theorem applies no matter what the distribution of the values in the population is, no matter what the shape of that is. Those might be normal or might not be normal. You can still use the central limit theorem either way. So you can always use the central limit theorem whenever you're drawing a sample at random with replacement that's large enough. And then if you want to know about the average of the values in the sample, the central limit theorem tells you something. The sum. Yes. Okay. The central limit theorem is about the sample mean. At least that's the way I like to think of it for purposes of this class. If I draw a sample of a size 100 and I want to know the sum of the values in there, that's 100 times as large as the mean. So it's going to have the same shape as the sample mean. The sample sum has the same shape as the sample mean. It's maybe 100 times bigger, so it's located in a different spot, but it has the same shape. Okay, so central limit theorem is true for the sample mean. That's how we'll usually use it in this class. It also tells you something about the sample sum if you wanted to know that. Do you use a 10% rule? No. I know what you're asking. You're asking what counts as large. And this is not a black and white situation. There is no cutoff where you can say above that cutoff, the sample is large and below it, it's not large. What this statement is saying is it's an approximate statement. It says the distribution of the sample mean is roughly normal. It's approximately normal. How good an approximation is that? The larger your sample size, the better an approximation. So if you have a really small sample, you had a sample of 5 individuals, then maybe it wouldn't be such a good approximation. But typically in practice, we have larger samples. We have large enough samples that usually you don't have to worry about this too much. You get a pretty good approximation to the normal distribution, and we don't worry about it.
Hey, Professor Wagner, can I say something here?
Please.
In a math class, this is the answer that we'd give. But in data 8, we have much more power. Since you have the original sample, right, you can bootstrap the sample mean, and you'll get something that kind of looks like the distribution of the sample means. If that thing isn't bell-shaped, you know your N isn't large enough. Your sample size isn't large enough. Right? You've got a computer. So you can actually use the power of that computer to just see roughly what this distribution is going to look like. So if you're concerned, is my sample size large enough or not, just go ahead and bootstrap the thing. And then if your eventual empirical distribution of your bootstrapped means looks wonky, then don't proceed any further. Say, I don't think this works. That's one way of approaching this.
Thank you. I love learning new things. Okay, so the central limit theorem, one of the things that many people find odd or confusing or strange about this is that it talks about the distribution of the sample mean. And your first reaction might be, distribution? What do you mean distribution? I've got a sample sitting in front of me and it's got a mean, that's a number. Why is there a distribution? So let me talk you through what I mean by that distribution of the sample mean and why there's a distribution. If I'm a data scientist and I draw a sample, I've only got one random sample and it only has one sample mean, and that's all I got. That's all there is for me. But that sample depended on random choices, and those random choices could have been chosen in a different way. So the sample could have come out differently. I could have ended up with a different sample than the one that I actually got. In some parallel universe, might have gotten a different sample. And so that means that then in that parallel universe, we would have gotten a different value for the sample average. So the sample average is not fixed in advance. It's a result of the random choices that we make when we draw the sample. And as a result, that means that there are many possibilities for what you could have gotten for the sample average. So that's why there's a distribution. It's the distribution of the possibilities that could have happened. Another way to think about that is to imagine before you've drawn the random sample, I'm about to draw the random sample, but I haven't yet. Then there's many possibilities for how that random sample could turn out. And so many possibilities for what the sample average could be. And that's why there's a distribution. There's a distribution of what those possibilities could be. And the central limit theorem talks about that distribution, those possibilities for the sample average. Okay, so what is that? How do you get that distribution? The theoretical answer for how to get that distribution could be, you take all possible samples you could have gotten, all ways you could have chosen who is in that sample. There are lots of possibilities. For each, you compute an average. So now you get a whole bunch of numbers. And then we look at the distribution of those numbers. All right. And that's the distribution of the sample mean. Okay. Good in theory as a thought experiment, but you can't actually do it in practice because there's too many possibilities typically for how the samples could have come out that you just can't list them all. So instead, we have to use something like the bootstrap, the empirical distribution, to approximate it. So let's walk through this. I already ran the cells because some of these cells in this notebook take a long time to run. Okay, so let's look here. I'm going to walk through the same example we did on Monday. We've got flight delays. In this case, we happen to have the entire population, so we're going to simulate what it would look like for a data scientist. That's going to give us both the God's eye view and the data scientist view. That's going to be handy. So here's the God's eye view of the entire population. The delays have a distribution that look like this. with a population mean of 16.6 and a population SD of 39.5. But the data scientist wouldn't know that because the data scientist, you in real life, would not have access to the full population. So we're going to simulate what the data scientists would see if they take one sample. They take one sample, and then they take the mean of the flight delays of the flights in that sample. Okay, so what we were doing on Monday is we then took 10,000 simulated samples and we looked at the histogram of those averages. And you got this approximately bell-shaped curve. Now, that's not all the possible samples. That's just 10,000 samples. If I had tried to enumerate all possible ways to choose a sample of size 400, well, there's 13,000 flights in this data set. And so I would need 13,000 times 13,000 times 13,000 multiplied by itself 400 times. That's how many different choices there are. In other words, number of possible ways to obtain a random sample. And here's that number. That's a ridiculous number. That's like gazillions and gazillions and gazillions. There's no way, even with a computer, that I can list all of those possibilities or run through all those possibilities and compute all the different sample averages I get from each possibility. All right. So in practice, I can't actually implement this thought experiment. So what did I do instead? Instead of listing all samples, I chose 10,000 random samples, and I figured they'd be representative of the set of all samples. So you see how this is a kind of like similar, like a bootstrap like idea. It's we're using the a sample as a representative of the entire population, but now here we're talking about 10,000 samples out of the set of all possible samples. In other words, 10,000 sample averages out of the set of all possible sample averages. Okay. So that's why there's a distribution of sample means. Now, the central limit theorem predicts for us what that distribution is. It predicts for us that the shape of that distribution is roughly bell-shaped. It's a normal curve. A normal curve is specified by two things: the center and the width, the spread. The way we measure the spread is usually with the standard deviation. So let me just kind of talk you through what we discovered on Monday about what the center and the width of that bell curve is. So the center of that distribution is fairly easy to specify. In fact, it's a result of the law of averages. It says that this distribution of sample means is going to be bell-shaped, and it's going to be centered roughly at the population average. Okay, we kind of saw some examples of that on Monday. Now, what about the width or the variability of this distribution? Why do we care about this? Here's one of the key ideas for today's lecture. Why do we care about the width or the SD of this distribution of sample means? The spread or the width of this distribution helps me understand how much variability there is in the sample average. So I said it's centered around the population average, which is good. That's what we're trying to estimate. That's something we would like to have, an estimate to have, is it should be centered around the true value we're trying to estimate. But of course, any particular sample average most likely won't be exactly at the population average. It'll be somewhat above it or somewhat below it. How much above or how much below is determined by the width of this distribution or the spread of this distribution. Okay, so the spread of this distribution, or in other words, the variability of the sample average, is a measure of how accurate an estimate I've got. And the central limit theorem helps me predict this variability, this spread. And that's going to be useful because if I want an estimate with a particular level of accuracy, then I can use the central limit theorem to predict whether a particular sample size is going to be big enough to give me that level of accuracy or not, and to predict what sample size I need to ensure that I achieve that level of accuracy. So this comes up a lot, for instance, in statistical polls, where I'd like to estimate who's going to win the next election. And my poll is going to have some margin of error. And if I have in mind an idea of how large or how small I would like my margin of error to be, then I can use the central limit theorem to figure out how large a sample size I'll need. The central limit theorem says if you use a sample size of 100, your error is going to be this big. If you use a sample size of 400, your margin of error is going to be typically be about this big, smaller still, and so on. Okay, so this central limit theorem will help me understand the relationship between the sample size and some notion of typical amount of error in the estimate. And then I can choose how much money to spend. In other words, how large a sample to choose so that I achieve the desired level of accuracy. So I get the error level down low enough that I can tolerate it. I'll never get the error rate down to 0, probably. So it's about trading off between the cost of a larger sample versus the precision or the accuracy of a better estimate. And the central limit theorem is going to help me manage that trade-off. Okay, so let's look at that. Just a recap of what we did on Monday. We took samples of different sizes and we computed the distribution of the sample mean for those different size samples. So here I plotted an overlaid histogram where I did this twice. I did this experiment twice, once with samples of size 400 and once with samples of size 900. Okay. So take a look at this histogram and tell me, what does this histogram tell you about the effect of increasing the sample size, of a larger sample size? Lower SD, smaller variability, reduces the spread. Yeah. Larger sample size makes a narrower distribution, less variability. And that, from what we care about, that is a good thing because that means we're going to have a more accurate estimate of the population, SD. So here's my little check to see how you're all doing. Here's a discussion question for you all. I've got that same histogram, and I want you to, little Mad Libs for me, fill in the blank, not arbitrarily, not with the craziest, funniest thing, but with what's true. So the gold histogram shows the distribution of what? Values, each of which is what? All right, I'm seeing lots of votes for AD, some votes for BD. All right, a good amount of consensus. It sounds like we should figure out whether the first blank should be filled in with A 900 or with B 10,000. Someone talk me through a reason why A 900 looks like a sensible answer to fill in the first blank. I'm going to type in chat. You can see it as a legend on the graph. The gold one is the narrower one, so it must be 900. On the right corner, the yellow indicates 900. So let's talk through what that 900 represents. What is that 900? 900 is the size of the sample. Okay, good. So, okay, so you understand what that represents. Someone want to talk through for me a reason why you might put B 10,000 in the first blank? You type in the chat. Yeah, 10,000 is the number of simulated values. That's how many times we simulated this sample and take the average process. It's the number of repetitions. Yeah, so what are we histogramming? Maybe we should figure out what we're histogramming. We're histogramming an array of values. And how were those values filled in? They were the result of repeating this thing 10,000 times. In each simulated experiment, we drew a random sample and took the average, and that gave us a single number, and we added that number to the array. We did that 10,000 times, so we got 10,000 numbers, 10,000 sample averages. And then we took a histogram of this. So the correct answer is B, 10,000. Good job, everyone who answered that. Because what we're histogramming is 10,000 numbers. We have 10,000 numbers. Each number represents a sample mean, and that's what we're histogramming. So the 900 tells us something about how each of those 10,000 numbers was obtained. But the histogram is a distribution of 10,000 values. Yeah, tricky, tricky, tricky. Okay, the second blank is everyone who said D, correct, absolutely right. Each number in that array is a sample mean. It's an average of flight delays, an average of the delays for the flights that were in the sample. So that's good, that's good, all got that. How do I know the flights that I sampled, chose 10,000 samples? That was in my code. I was in my code, I did 10,000 repetitions. Yes, 900 is the sample size and 10,000 is the number of repetitions, the number of samples. Right on. Okay, good. Let me pause here for any questions or concerns or confusions about this.
David, can I ask a question?
Please do.
Supposing instead of 10,000, we had repeated the process 20,000 times, would you see a big difference to the pictures?
That is a great question. What do you think? I see some votes for no. I see some votes for taller and narrower. Anyone want to give me a reason for why you might say taller and narrower? Okay. I can see how you would come, yeah, that I can see where that's coming from, that I increased from 10,000 to 20,000. So that should reduce the variability, should bring you closer to the center. More repetitions means more representative. Want to give me a reason why you say no, it's the same shape? Sample size is the same. Sample size is what affects the variability, not the number of repetitions. You're right. You're right. You're right. So the correct answer is no. Changing from 10,000 to 20,000 repetitions would not change the look of this very much. Why? Because the central limit theorem says that the spread in this distribution depends on the sample size. It doesn't depend on the number of repetitions. In particular, the central limit theorem says if you could get the probability distribution, the exact distribution from looking at all samples, that would be approximately bell-shaped. We can't get from all samples, so we're only getting 10,000 or 20,000 of them, but that should give us approximately the right shape. So whether you have 10,000 repetitions, that's approximately the shape of the true probability distribution, or 20,000 repetitions, also approximately the shape of the true probability distribution, both of those will be approximately the same shape. There's some true underlying shape that we can't really compute, but exists conceptually. And 10,000 repetitions gets us close to that. 20,000 repetitions gets us maybe a little bit closer, but it's also close to the same thing. So they're going to look about the same. And 10,000 or 20,000 is such a large number that you're getting really, really close to the true distribution of the sample mean. Okay, so that was a little tricky. Okay, all right. So let me try another way of stating this, and I hope it's not going to add to the confusion. When I draw a sample of 900 from the population, that sample is sort of representative of the population. If I get a sample mean, that's like drawing a sample mean from the set of all possible sample means. So it has some distribution of all sample means. If I draw 10,000 sample means, that's like a sample from all possible sample means. So my 10,000 sample means should have a distribution that should be like representative of the set of all sample means. So the shape of the distribution of 10,000 sample means should be approximately the shape of the distribution of all sample means. Okay, hope I didn't add more confusion. Professor Ani, anything you wanted to add to that?
No, I just wanted to go a little bit further into the 10,000 versus 900, because it seemed like there was still some confusion about what each number is representing. Let me just say something. You know, have you noticed that when we do these simulations, we often choose 10,000 as a number of simulations? Have people noticed that? Sometimes in the textbook, because it do something 10,000 times. Why do you think that is? Because it looks like a nice round number. It's actually not. It's there's a reason for it, which it is a lot big enough for what? We think it's big enough so that the distribution that we see actually reflects the probability distribution that we're trying to get it to look like. But there's actually a sharper reason. 10,000 gives you a particular margin of error that I'll talk about next time. But the point is, the more repetitions you do, the more it looks like the underlying probability distribution, but that isn't changing. So once you've got past a certain level of repetitions, that the picture doesn't change very much. And this takes a little while to get used to. So I'm sorry, David, I interrupted you. But there are a couple of numbers floating around here, and hopefully by the end of Friday, people will have got a little bit of a handle on the two different numbers. There's actually three numbers, because there's a 400 as well on this graph. So the thing that people are saying, that if you have more draws, then the thing will get narrower and taller, that's the difference between the 400 picture and the 900 picture. The 900 picture is narrower and taller. You are right there. Okay, sorry, David. I'm done. I'll shut up now.
Not at all. That was wonderful. I am so fortunate to have you here, and to have, for us all to have a statistical expert here to help us talk through this stuff. Okay, so to summarize, the gold histogram was a distribution of 10,000 values, each of which is obtained from a sample of sample size 900. The blue histogram was a distribution of 10,000 values, each of which was obtained from a sample of sample size 400. So the 900 and 400 was the sample size, and 10,000 was the number of simulations we did. Both of these shapes are roughly bell-shaped, but the larger the sample size, the narrower the bell. Okay. Let's see. We can look through here. As a reminder, here's what we get. You can just take a look again and see what happens if we look at different sample sizes. Sample size 100, roughly bell shape. The width of this SD of the sample means is a little under 4. Sample size 400, same shape, but for bell shape, but the SD of the sample means now goes to 1.9. I'm showing you here how the width of this curve varies based on the sample size. It might not look any narrower because the graphing has changed the x-axis, but here it got even narrower still. The SD of the sample means went down to a little under 1.6. And the central limit theorem tells us exactly how that variability works. It says the distribution of the sample averages, let's call that the distribution of the sample mean. That's the distribution of all possible sample means that you could have gotten out of all samples, is approximately normal. And the central limit theorem tells us where the center of this is. It's centered at the population average, as we discussed. And we've just been working out the relationship of the SD of this. What we saw on Monday was that it decreases as you increase the sample size, not linearly, but according to the square root of the sample size. And the actual rule is that you can take the population SD, the SD of the population, divide that by the square root of the sample size, and that will give you the SD of the sample means, the width of this bell curve that is the distribution of sample means. So this now is what the central limit theorem says. It says what the shape is, what the center is, and what the spread is. So let's jump into the notebook. And I've been running something that took a long time to run. What I did was I repeated this experiment for a bunch of different sample sizes. And I computed the width of the bell curve that you get for each different sample size. So here we have sample sizes 100, 150, 200, so on, up to 950. And for each, I've computed what the width of the bell curve was when I used that sample size. So for sample size 100, we previously saw it was about 3.97. Here's for 150, it's 3.2. So this column shows me the SD that I got by doing this simulation with 10,000 simulated sample means. And then I've also shown in this table what the central limit theorem rule says. Okay, so the central limit theorem tells you that the SD of this sample means can be obtained by this formula, the population SD divided by the square root of the sample size. So I put what you get from the formula in this last column. So we're comparing what we got from our simulation versus what we got from our mathematical formula here. And you can now eyeball these. How good does the formula look? How good is the agreement between simulation and formula? Good agreement? Bad? Good. Very close. Yeah, very good. Very close. Like 3.97, 3.94, that's pretty close. Or if we look down here, 2.0, well, 2.1 and 2.11, that's quite close. Another way to look at this, instead of looking at the numbers, is to visualize with a scatter plot, where we have in the blue, we get the results from the simulation, and the yellow is the results from the formula. And you can see just how close these are. These dots are very, very well aligned. Okay. So what this is showing you, this is hopefully giving you some confidence in the central limit theorem. The central limit theorem is something that can be proved mathematically, but the mathematical techniques are beyond what we can show you in this class. So instead, I'm trying to give you some confidence in the central limit theorem by showing you that it matches up with what we obtain by simulation. You're absolutely right. You notice that this formula requires you to know the population SD. This is a great point. If you don't know the population SD, how do you use this formula? Well, the short answer is, oh, you can't. But there's a longer answer. And you're absolutely right. Your questions are so spot on. If I'm kind of doing all this sampling stuff because I don't have the whole population. I don't have the whole population, so I can't compute the population SD. I'm doing the sampling stuff because I want to estimate the population mean. I don't have the population mean. So if I don't have the population, I don't have the population mean. Why would I have that population SD? I probably wouldn't. But let me come to the rescue. What we're going to do in practice. Remember, we're taking a sample. From that sample, we can estimate the sample mean, which is our estimate of the population mean. We can also get the sample SD, the SD of the numbers in that sample. And that's a pretty good estimate of the population SD. And so you could now use this formula with your estimate of the population SD in place of the true population SD. We don't know the true population SD, but we'll take our estimate and just use that instead. And if your estimate is pretty good, then this formula will give you a pretty good prediction. Okay, so that's what you could do in practice. You don't have to do that. If that feels a little dodgy, that's okay. You don't have to do it. The other way you can think of this is just telling us conceptually what's going on, even though in practice we won't know what the population SD is. This is telling us conceptually what the relationship is. And so that's helpful because it helps me understand what the effect of increasing sample sizes. That's another way to think about why the central limit theorem is useful. Did that help? Did I answer your questions? That was a really insightful question. Please follow up if it didn't. Okay. Thank you. So glad you asked that. That was a great one. Let's do another demo. What about the central limit theorem? I've been working with only one data set. So I somehow haven't really shown for you viscerally just how powerful this central limit theorem is. I want to help you sink in the fact that the central limit theorem applies no matter what the distribution in the population is, no matter what the data set is. So remember, for the United flight delays, the distribution in the population was not normal, but didn't look like anything. It was just some particular shape there that's not some special shape that we're used to. And yet the distribution of sample means was bell-shaped. And there's nothing specific about this one data set. There's nothing special about this data set that I got a bell shape. The central limit theorem says you're always going to get a bell shaped, no matter what the original population was, no matter what its distribution was. So for instance, let's look at another data set. I just picked another random one. We were looking at one point at salaries of employees in San Francisco. So here's a histogram of their salaries. Does that look like a normal distribution? No, not really. It's just whatever it is. So that's the population distribution. We could then repeat all the same things we've been doing with the flight delays, but now do this for this San Francisco salaries. Take a mean, take a sample, take the sample mean, the mean of the salaries of the people in the sample. We could look at the distribution of that sample mean. We could approximate it with the empirical distribution obtained by simulating 10,000 times. We could draw a histogram. Well, we could if I hadn't made some error here in my code. What error did I make? Sampled flights is not defined. Sampled flights. Well, I've got a typo in my code. No wonder this didn't work. All right, this process is going to run for a little while. What shape do you expect the distribution to have, the distribution of sample means to have, if the central limit theorem is true? The normal distribution. So let's see if that's what we get. I think this computation is taking a while, so maybe I'll continue on my slides and we'll check back in 30 seconds or so. All right, so let's do a discussion question and then we'll check back. Here's your discussion question to test and see how you're doing with central limit theorem. We got a city with 500,000 households. We care about the income of each household, and the average income in this city is $65,000, and the SD of those incomes in this city is $45,000. Then what do you think is true about the distribution of the incomes? Yes, C is correct. Good job. Good job. All right, this is a little test. Central limit theorem tells us about the distribution of sample means, but this question is asking about the distribution of all incomes in the city. What's the population here? The population are the 500,000 households. So when it asks about the distribution of incomes, that's asking about the distribution of those 500,000 incomes. In other words, this is asking about the population distribution. There was no sample here. Since there's no sample mean, there's no central limit theorem. Actually, nothing we've been talking about with the central limit theorem is relevant to this at all. This was just a big trick question. This question is asking about the population distribution, and the population distribution might be anything because the question didn't tell us anything about the population distribution. In fact, in most cities, typically the distribution of household incomes is not bell-shaped. It's not normal curve. There's a small handful of households that have a very large income often, for instance. Okay, good job, everyone who picked C.
Wait, hang on.
Yes.
Can I disagree?
Please.
So I'm looking at this distribution, and it has an average of 65,000 and an SD of 45,000, and I feel that we never use that. I think we should use it. I think we should. We don't need Chebyshev. What I'd like you to remember for the normal curve, if you go average plus or minus 2 SDs, does anybody remember what proportion you pick up? You pick up 95%, yes. Average plus or minus 1 SD is 68%, average plus or minus 2 SDs is 95%, and then average plus or minus 3 SDs is 99.7 something percent, okay? So I feel that when somebody asks me, is the distribution normal or not, what I'm going to do is I'm going to draw the normal distribution with this mean and this SD. Right, so if I draw the normal curve, then the center is going to be at 65,000, right? Plus or minus 1 SD on the right-hand side, I'm going to end up at 110,000. On the left-hand side, I'm going to end up at 20,000, right? If I go 1 SD below that, then where will I get? I suddenly have negative incomes. And that really bothers me. Right? So I don't think it's possible for incomes to have a distribution that is normal with these two numbers. So I think in this case, the better answer is B. Right? You actually, so if you actually, yeah, it is right skewed, exactly. That big spread is coming from somewhere. It is not coming from the left-hand side because you're blocked at 0. So it's coming from somewhere. And the guess is, it's coming from a right tail. But you can say, I think, very confidently, this is not normal. So when somebody asks you, is a distribution normal or not? And like this, as Professor David said, this is not, there is no sample, there is no central limit theorem. This is just a distribution of 500,000 incomes, right? Somebody asks you, is it normal? Is it not? My suggestion is always draw the normal curve, put down that mean, and go 2 or 3 SDs on either side. Right? And if you're hitting impossible numbers, which is what happened here, then you can say, no, it's not normal. If you are not hitting impossible numbers, then pick C. Right? Because maybe, I mean, you're not getting into nonsense, but you still don't know the shape of the distribution. But when you have some summary statistics, it's a very good idea to try to use them if possible. So I would stick my neck out and say this one is not normal.
Thank you so much, Professor Ani. You saved me. I was just skating along here. And this is, as someone said, a trick within a trick. It's a double trick question, and I got and it got me.
Yeah, it just takes a long time to get used to, which bits of information are going to be relevant for doing what. How many SDs should we look for? Oh, with the normal curve, you see, you're only trying to test, the question is only, is it normal or not? So with the normal curve, if you go out to 3 SDs on either side, you pick up almost everything, 99.73. So you don't need to go out any further than that. Wouldn't there be some complications with close to normal? Yes. So, I mean, not close to normal. I don't think this is anywhere near close, right? You cannot go even 2 SDs below normal. So you wouldn't call that close to normal at all. And I understand that these words like close and approximately and large and so on are unnerving because, they aren't hard and fast limits. Okay, so the question is, can households have negative incomes? And usually the income is not measured as a negative number. You can have net worth that is measured as negative number. How do you know what the values of 1 SD, 2 SDs, and so on are? That was on a slide. I think, Professor David, you had that slide on Monday. There was a slide that said for a normal curve, if you go 1 SD on either side of the average, you have 68%. I'm remembering correctly, right?
Yeah, we said that if you go plus or minus 2 SDs, then you capture 95% of the data if the data is normally distributed. Yeah. So
there's a slide from last time's lecture which compares Chebyshev's bounds. Chebyshev has, it has to be at least this much. But if it's normal, you know that it's going to be approximately a certain amount. And I think that's where the 95% numbers is coming from. Sorry to interrupt again. But you can see I'm a little attached to calculations involving averages and SDs.
So glad you caught me, corrected me there. Okay, so let's go back to our demo. We were looking at what the shape of the distribution of sample means is for a different data set. And this is the payoff that I wanted to show you. Look, we got a totally different data set that had a totally different distribution in the population. And I computed a bunch of sample means, and it's still normal shaped. So this is one of the things that's powerful about the central limit theorem is it doesn't matter what the distribution of the data in your population is. You can still use the central limit theorem. The set of sample means, the distribution of sample means will still be normally distributed. Okay, so reminder of the central limit theorem. So you have it all in one place. If you have a sample that's large and drawn at random with a replacement, then no matter what the population distribution is, the probability distribution of the sample mean is roughly normal. It's bell-shaped. It's centered at the population mean, and its SD is the population SD divided by the square root of the sample size. All right, I am going to leave you a discussion question that you could think about as you walk off to your next class. Suppose you had a population with an average of 70 and SD of 10. Which one of these histograms below could be empirical distribution of 10,000 simulations of sample means if the sample size is 100? I'll let you think about that one. We'll stop here and I will see you on Friday. Don't forget to work on your project and submit your homework this week. Take care.